Hi, I'm Feng Zhenan. In this video, I will talk about our paper, A Privacy-Preserving Framework for Cloud-Based HVAC Control. Cloud-based control architecture has been widely used in different applications, such as building automation. In this picture, a smart buildings exchange information to a cloud-based controller. However, privacy is a significant concern for the user of the cloud-based control systems, as cloud controller may act as honest but curious adversaries and attempt to infer private information based on the sensor measurement of a system. To demonstrate the potential privacy violation in a cloud-based HVAC control system, we perform an experiment wherein a neural network-based occupancy estimator was trained for a building using its CO2 measurements and occupancy data. In our experiment, the CO2 measurements were generated using the transit simulator. We can see that the true occupancy of the building can be closely tracked using the CO2 measurements. According to our experiment, the occupancy can be estimated with an accuracy of 92.1% using the sensor measurements. So, to enhance the security of the cloud-based control system, encrypted control has been applied to these systems. In this approach, the sensor measurements of systems are first encrypted, and the cloud controller receives the encrypted sensor measurements. Thus, the cloud controller cannot infer sensitive information from the encrypted measurements. However, as this figure shows, encryption will increase the data size. Due to the communication and heavy computations of encryption, both sensor side and cloud sides will have high power consumption. Also, the computation is really expensive. So, we propose a privacy-preserving cloud-based HVAC control framework to ensure the occupant's privacy, at the same time, reduce the communication and computation burdens of the encrypted HVAC control. First, we use an RC network to model the thermodynamics of a building. Here, we take the temperature model as example. The thermal model is nonlinear due to the product of control input and the state variables. So we use the feedback linearization, and we can obtain a linear stochastic system. Then we form the model predictive control problem as follows. To solve the MPC problem, we transfer it into equivalent optimization problem. The temperature measurements are encrypted using the CKKS encryption scheme, and the controller receives the encrypted measurements and compute the required MS flow for regulating the temperature. The optimization problem can be solved by encrypted projective fast gradient method. To reduce the high communication and computation costs of fully homomorphic encryption, we introduce an event triggering unit to decide whether the system communicates the encrypted measurements with the cloud. Here is the overview of our encrypted event trigger control system. The event triggering unit has two actions. When AT/IT equals to 1, the system sends the states to the controller. When AT/IT equals to 0, the system stops communication. Here, IT denotes all available information to the event triggering unit. For example, like last states, last action. Also, to prevent the event triggering unit from always opting out of communication, we impose an upper bound on the time interval between two triggering instances. LT denotes the number of samples since the last communication between the system and controller. If LT is more than the threshold level, TS, the event triggering unit, communicates the states to the controller. This figure shows the time evolution of LT. The optimal design of the event triggering policy can be formulated as the optimal control problem as follows. The first part is denotes the control cost, and the last part is the communication cost. Well, the number is a positive number. The event triggering unit receives a penalty equals to lambda if ATIT equals to 1. Yeah, optimal control problem. The control policy may only depend on a subset of available information to the decision maker rather than all the available information. We show that the necessary information for decision making are current state, last communicated state, time since last communication. Since the optimal design problem is not Markovian, hence we design a new state YT and get the new system dynamic. Then we can use reinforcement learning to obtain the best policy for the proposed event triggering unit. We tested our proposed framework by using Transys and Python as co-design. We built a 4-room building with an HVAC system in Transys and implemented the event-triggered MPC using Python to control the indoor temperature of 4 rooms. We use 23.5 Celsius as the reference temperature. The range of comfort temperature is between 22 Celsius and 25 Celsius. The sampling time was 5 minutes. We used 2 metrics to study the impact of different event triggering policies on the performance. The total violation for the temperature is defined as the percentage of time instance where the temperature of at least one zone is outside the comfort temperature band. The maximum violation for temperature is defined as the value of the largest deviation of temperature from the comfort band among all zones and all time instances. We use communication rate as a matrix to study the impact of the optimal and threshold-based event triggering policy on the communication frequency between the system and the cloud. We can see in Figure A, the percentage of the violation is significantly lower under the proposed optimal event triggering policy than the threshold-based policy. For instance, the percentage of violations under the optimal policy is 5 times smaller than under the threshold-based policy when the communication rate is around 37%. Also, the proposed optimal triggering policy achieve a smaller deviation compared with the threshold-based policy. This figure shows the communication rate of the optimal triggering policy as a function of the communication penalty lambda. According to this figure, the event triggering unit communicates less often with the cloud as the communication penalty becomes large. Based on the above figures, the percentage of violations and the maximum violation are relatively large when the communication rate is less than 36%, which corresponds to lambda larger than 51. We believed the lambda equals to 51 leads to an acceptable balance between the control performance and communication rate. Then, we compare the total size of data which was communicated between the building and the cloud as a function of times in 3 cases: unencrypted periodic control, encrypted periodic control, and the optimal event triggering policy with lambda equals to 51. According to this figure, The encrypted periodic control increased the size of the communicated data by 170% compared with the unencrypted periodic control. This is particularly a major issue when wireless sensors are used, since the communication unit of a sensor accounts for the majority of power consumption of a wireless sensor. Our proposed event triggering unit reduced the required computation resources for solving the encrypted MPC by more than 60%. We can see that our proposed framework not only ensures efficient control of the indoor temperature, but also reduce the computation and communication cost. That's all of the video. Thanks for watching.